Good afternoon. In our CE 224 dynamics class, we will finish up the kinetics of the particle. And our last subject, it was impulse and momentum. Last week we did the part 1. Right now, in this week, we are gonna do the part 2 and we are gonna finish up. And the subtitle is angular momentum. The angular momentum is the angular momentum of a particle about point O is defined as the moment of the particle linear momentum about the O. Since this concept is analogous to finding the moment of a force about a point, the angular momentum at zero is sometimes referred to as the moment of momentum, because we are taking the moment, right? Is our momentum's moment, which is denoted by HOZ direction is d, the distance, multiplied by the mass and velocity. The scalar formulation is if a particle moves along a curve lying in the xy plane, as this figure here, as you see, the angular momentum at any instant can be determined about point O. In this point, actually the z-axis, in z-axis, right, in like right hand rule, by using a scalar formulation, which is the magnitude of h0 is the meter, kilogram, and meter per second. So it's gonna be kilogram meter square per second. The vector formulation: if the particle moves along a space curve figure in this figure, the vector cross product can be used to determine the angular momentum about O. So it's gonna be the R, the vector quantity in XYZ direction, cross product of MV, the momentum. So it's gonna be what it is. It's gonna be moment of the momentum. As we know, if it is cross product, M is constant. You can take it out if you want, but it's gonna be Rx, Ry, Rz in IJK direction, and then we are gonna write it M velocity in X direction, velocity in Y direction, and velocity in Z direction. How we were doing, like we were taking constant I, we will do this one, and then we will cross product and then subtract each other. Then we are saying minus J is Rx multiplied MVZ minus Rz multiplied by MVX, and plus K is gonna be Rx multiplied MVY Ry minus Ry multiplied by MVX. So it's gonna be the cross product of this angular momentum. Here R denotes a position vector drawn from point O to the particle, as shown in the figure. H0 is perpendicular to the shaded plane containing R and MV. In this shaded plane is gonna be perpendicular. How is gonna be perpendicular? Is gonna be inside or outside, right? In order to evaluate the cross product, R and MV should be expressed in terms of their Cartesian components, so that the angular momentum can be determined by evaluating the determinant. Let's investigate one example. Determine the angular momentum at zero of the particle about point O. So we have a particle over here. We have an origin O here. So we are gonna calculate the angular momentum. How we are gonna do? We are gonna calculate the R, the distance R. We have all the components, as you see, X, Y, Z. we are gonna define our R, then the M is given 1.5 and V is given in what direction? X direction, right? So, okay. All right, we will calculate the angular momentum of this particle, which is 1.5 kilogram particle. As you see, it's moved from point A to B, and as you see, from O to B, there is an perpendicular distance, so orthogonal distance. So we can calculate it very easily with this particle's motion with this intersection, which is ROB is equal to minus 7 in y direction, so it's J. So R is gonna be minus 7 J. And for the velocity, the magnitude is 6 meters per second, but we need to find the velocity unit vector, which is U is equal to, as you see, for the x direction is from -2 to 0, which is in positive direction. The motion is positive direction, so it's gonna be 2I, because it's gonna goes from -2 to 0. Then for y direction, it's gonna go from -3 to -7, so it's gonna be -4 in J direction, plus Z direction is going from 4 to 0, so it's gonna be minus direction, so it's gonna be the 4K is gonna be my vector of motion, and divided to magnitude of this vector, which is 2 square plus minus 4 square plus minus 4 square, and we need to take the square root of it, which is 1 over 2. Is going to be our unit vector. For velocity vector, we will multiply by the velocity magnitude, which is 6 multiplied by u, which is unit vector of the velocity. So when we find this r, which is also vector quantity, we are gonna find the angular momentum as r cross product of mass, which is constant, is a scalar quantity, multiplied by the velocity vector. All right, here is calculated over here, as you see, the same thing, and velocity vector is 2I minus 4J minus 4K, and we need to make a cross product of minus 7J. So we are gonna write it down. H0 is equal to IJK. I is 0 for R, because we are gonna plug here the ROB. 0 minus 7, 0. Then for mass multiplied by velocity product is mass is 1.5 multiplied by 2 is gonna be 3 in I direction. 1.5 multiplied by minus 4 is gonna be 6, minus 6 over here, minus 6 here, and minus 6 over here, and 3 here. Then after that, we are gonna calculate I vector. Minus 7 multiplied by minus 6 is gonna be 46, minus 0 multiplied by minus 6 is 0. So it's gonna be 46, 42 I, which is here. Then we are gonna calculate J is gonna be minus, and then we are gonna 0 multiplied by 0, minus 6 is 0, minus 0 multiplied by 3 is 0, so it's gonna be 0. J quantity is 0. There is no. Then we are gonna calculate K values. k values is 0 multiplied by minus 6 is 0. Minus 7 multiplied by 3 is gonna be minus 21, but it's gonna be 0 minus 21 is gonna be plus 21, so 21k. So we find our angular momentum as 42I plus 21k kilogram meter square second. Okay, let's depict the relationship between moment of force and angular momentum. We know that force is equal to mass multiplied by acceleration, which is the first derivative of velocity with respect to time. The moment of the force about point O can be obtained by performing a cross product multiplication of each side of this equation by the position vector R, which is measured from the XYZ inertial frame of reference. We have, which is the moment of a force is equal to R, which is the position vector cross product of force, which is, as we show here, R cross product of M, the first derivative of velocity. When we open up the angular momentum, and if we take the derivative of it, so ddt h0, because we write it h dot is going to be the first derivative of angular momentum with respect to time. It is d over dt r mv, right? The momentum multiplied by the r cross product of momentum, which we said moment of a momentum. So if we use the chain rule, first we are gonna say r dot, which is the first derivative of the position with respect to time, cross product of the mass multiplied by velocity plus the position vector cross product of mass of particle and the first derivative of velocity. Now, here we can say that if we take into account this guy, so we know that V is dr over dt, right? So it's gonna be r dot. We know that one. So especially this one is gonna be r dot cross product of m r dot. M is constant, so let's take it out. So it's gonna be m r dot cross product of r dot, which means this one, these two vectors is same, so it's parallel to each other. If you have parallel line like this, if you make a cross product, if there is no intersection, so this means it's zero, right? There is no perpendicular to each other, so it's not dot product anymore. It's gonna be cross product, which is perpendicular line we are measuring. So the first term of this guy, here is goes to 0. So what it means, our R cross product mv dot, which is our moment of a force, is equal to h, the angular momentum's first derivative, which is total moment of force is equal to h0 dot, as we see here. And the total force is L dot, which is L is our linear momentum, right? Linear momentum, which is m multiplied by the velocity, mass multiplied by velocity. So the first derivative is gonna give us, as you see here, is total force. If you look at the principle of angular impulse and momentum, is rewritten in the form of the total m0 dt is dh0, because we know that total m0 moment of force is equal to h0 dot, right? So which dot is dh0 over dt. If you take this dt on left side, it's gonna be m total m0 dt is equal to dh0. And integrated, assuming that at time t is equal to t1, h0 is gonna be h01, and time is equal to t2 is gonna be h02. Then we will have total of from t1 to t2 integral of m0 dt is equal to the angular momentum, the final position angular momentum minus first position initial value of angular momentum. And if you rearrange it, you are just gonna put in this form here the initial angular momentum plus the total moment of force integral is equal to the final form of angular momentum. The last thing is conservation of angular momentum. Angular impulses acting on a particle are all zero during the time t1 to t2. This equation is known as the conservation of angular momentum. Then we are gonna say this the total all of the moments from t1 to t2 is zero. Then it's just h01 is equal to like the first angular momentum is equal to the final angular momentum, and also the total of first initial angular momentum is equal to total of, as a system, if you think, total of final angular momentum. Let's jump to questions and we will understand all this concept better. In this question, we have two identical 10 kilogram spheres are attached to the rod, which rotates in the horizontal plane. The spheres are subjected to tangential force of 10 Newton, and the rod is subjected to a couple moment m, which is 80 Newton meter, where time is in seconds. We are gonna find the speed of the spheres at time is equal to 4 seconds if the system starts from rest. Okay. We have a formula of, we know that it's zero initial angular momentum plus the integral of from time 1 to time 2 the total of moment, force of moment dt is equal to the final angular momentum. We know that one. We know that it starts from rest, so the first initial velocity is zero. That means there is no angular momentum, so this guy is equal to zero. So we need to open this term. What we had these two poles, the couples and the rod. How we are gonna do? We have two poles, right? Two identical couple of it, and from 0 to 4 seconds is the integral, and we have the force acting on it is 10 Newton F multiplied by R in order to get the moment, which is 0.5, and we need to make it dt plus, because that act is not ended, because we have also the rod is subjected to a couple moment of 80 Newton meter. So we are gonna say 0 to 4 8t dt is equal to the final angular momentum, which is we have two spheres multiplied by 0.5, which is the radius, right?
and multiply by mv, which is m is 10 kilogram, and the velocity we don't know, which we need to calculate it. Let's say v2. So if we do this term, is gonna be 10 t from 0 to 4 plus, if we take this guy, is gonna be 4 t square from 0 to 4, and it's gonna be equal to 10 v2. So if you do these terms, it's gonna be 40 plus 16 multiplied by 4 is gonna be 64. It's gonna be 10 v2. So it's gonna be 104. So v2 is gonna be equal to 10.4 meter per second, which is our answer, which is the final velocity of these spheres at time is equal to 4 seconds. Similarly, but right now we have the 4 spheres of 5 pounds, and is rigidly attached to the crossbar frame, which has a negligible weight of these rods. A moment x on the shaft is shown is 0.5 t plus 0.8 pound-feet. We are going to find the velocity of the spheres after 4 seconds starting from rest again. Then we have the conservation of momentum. The initial angular momentum is equal to plus the total of from t1 to t2, the initial to the final times moment of force dt is going to be the final angular momentum. Directly we can say this guy is goes to 0 because the velocity is 0 because it starts from rest. And in order to find our moment, total moment is given here. So it's gonna be from 0 to 4, 8t, sorry, 0.5t, 0.5t plus 0.8 dt, right? This guy. So we have in the right hand side 4 spheres we have, which has 5 pounds. So what are we gonna do? It's gonna be 5 over 32.2 in order to find the mass of these spheres, right? We need to divide it into gravitational force. The velocity we don't know, so it's gonna be velocity, the second velocity, and the distance, which is 0.6. That's it. So we find this guy is here, this term. So we set up our equation. Let's take the integral. We know that 0.5 over 2, 0.5 over 2, which is 0.25. 0.25 t square plus 0.8 t from 0 to 4 is equal to, so this term, these calculations, let me calculate and come back. Okay, it is 0.373, and when we plug here 0.25 t square is gonna be 16 plus 0.8 multiplied by 4 is gonna be, this one is v2, and 0.373 v2. When you do this calculation, you will find the final velocity as 19.4 feet per second. So we found the final velocity of this system. Alright, then we are done.